right, we're going to pick up then talking about continuing the chemistry of life notes in your notes packet, and we're going to talk about acids and bases. So to understand acids and bases, you have to know just a little bit of basic chemistry and understand what ions are involved. So these are ionic compounds that when I throw them in water, they break up into the ions that formed the ionic compounds. So when we look at an acid is anything that when I throw that acid, or that when that acid is dissolved in water, it releases hydrogen ion and some nonmetal, okay? Or some polyatomic ion. So if we're looking at sulfuric acid, for example, sulfuric acid has the formula H2SO4. If I throw that if it's in a solution, which it always is, it forms hydrogen ion, so H plus will be separated from the from the compound, and sulfate ion, SO4, will be with a negative charge, will be separate in solution. So that hydrogen ion, the number of hydrogen ions that are released indicates the strength of the acid. For example, if I put water in water, so that's just water in its ionic form, hydrogen ion breaks off of water, so one hydrogen ion is floating around in solution, so that's H plus, and then we have OH minus, which is floating around in solution. And hydroxide ion, which is OH minus, that leaves a basic environment. So anything that contributes hydroxide ion, we call a base. And anything that releases hydronium ion, or H plus, we call it in biology. If you were taking a chemistry class, you'd call it hydronium ion, H3O plus, but we're going to call it just H plus. So anything that releases H plus, we call an acid. Anything that releases OH minus, we call a base. So water releases H plus and OH minus. So it releases equal amounts of H plus and equal amounts of OH minus. So if it's acid base together, what happens when we have acid and base together? What is the pH? 7. It's neutral. So when you have equal amounts of positive, negative, hydrogen, hydroxide ion, we say that that solution is neutral. But if I have hydrochloric acid, which is HCl, and I put that in solution, that's going to break up into H plus and Cl minus. There's nothing to balance that H plus. The Cl minus does not neutralize the H plus, so that's an acid because I have excess H plus in the solution. And pH is just a measurement of how much of that H plus is in the environment. So again, if I look at water, when that breaks up into its parts, we have this hydronium ion, which there's an extra H plus, right? And then hydroxide ion, but they cancel each other out, so water is neutral and has a pH of 7. So anything that has a pH higher than 7, we call a base, and anything that is lower than 7, we call an acid. So the lower the pH, the more acidic that substance is. So the pH scale is a measurement of the hydrogen ion concentration. So there's a formula we apply to it. It's the negative log of the hydrogen ion concentration. So if I look at something that has a concentration of hydrogen ion of 10 to the negative 7, the pH we assign is 7. So the negative log, if you did the mathematical workup on your calculator, or you just take the negative sign off of that exponent, and that's the pH. Okay, so what would the pH be if I said the hydrogen ion concentration was 10 to the negative 4? What's the pH? 4. So you just take the negative sign, whatever that exponent is, that's the pH. And now if you think about that number, and you look at the pH scale, and let's just, I'm going to switch to this so I can still record. Let's think about if I have a substance, if I say that the hydrogen ion concentration, and the symbols we use for that is this. If I say the hydrogen ion concentration is 1 times 10 to the negative 2, and I have another solution that has a hydrogen concentration of 10 to the negative 5, what does that mean? So let's analyze that. If you remember your math, 1 times 10 to the negative 2, so you're taking the number 1 and you're moving the decimal point 2 places to the left. What is that value then? If I take this and go 2 places to the left, I have 0.1, and then another place to the left would be 0.01, right? That's what 10 to the negative 2 means, correct? All right, so what does 10 to the negative 5 mean? I've got 1, and I go, so the decimal point is here, I go 5 places to the left. So I go 1, 2, 3, 4, 5, and then I drop my decimal point, right? So here we are, 1, 2, 3, 4, oops, I was here. So I go 1, 2, 3, 4, 5. Drop my decimal point, right? Basic math, but maybe for some of you it's been a while, or maybe math is not your strong suit. Okay, so which of these is a bigger number? 0.01 or 0.0001? Which is the bigger number? 0.01, right? So if I look at this and someone asked you, if I have a solution that has a pH of 2, so when I look at this, again, pH, you should write this down too, because I'm not writing this down for me, right? I'm writing it down for your guys' benefit. So a pH of 2 means this, and what is the pH here on this one? For this one, is pH what? 5, okay. So if I'm comparing this, so this is solution A. Solution A has a pH equal to 2, and solution B has a pH equal to 5. How much more acidic is solution A than B? Which one is more acidic? Solution A, right, because it has the higher number of hydrogen ions. It has 0.01 hydrogen ions. This one has only 0.0001 hydrogen ions. So this is much more acidic. How much more? Solution A is how many times more acidic? This is all based on tens, right? So how many more zeros do we have here than we have here? 3. So when I add 3 zeros, how many times more acidic is that? No, it's based on tens, right? So 10 times 3 is, not 10 times 3, 10 times 10 3 times is 1,000, right? So it's 1,000 times more acidic than solution B, because we're comparing 0.01 to 0.00001, right? So this one has 3 more zeros, so 3 zeros on a 1 is 1,000. So what if I have a solution, if I have a pH of 5 versus a pH of 3? What can I say? pH of 3 is how many times more acidic than a pH of 5? Say it louder. 100, right. It's 100 times more acidic than pH of 5. Okay, so this value of pH, the lower the number, the much more acidic the substance is. And it's all based on tens, okay? So we have to really respect those pH differences, right? If I tell you we're going to work with a solution in lab this week and it has a pH of 1, that's a pretty acidic substance, right? Compared to water, So pH of 1 versus pH of 7 of water. So we're talking 6 zeros times more acidic. That's really acidic. So that would be dangerous. That would be corrosive to skin. You wouldn't want to get it in your eyes. You'd be blind. So very, very strong substances. Okay, so just know that mathematical relationship between the values of pH. It's just zeros, okay? So simple subtraction, and then add that many zeros after the 1. The lower pH is that many more times. So there's a difference of 2 here. 5 minus 3 is 2, so add 2 zeros to 1, and that's the number of times more acidic it is. Okay, so going back, wherever I was, here we go. So if I look at this pH scale, it starts at 0 and goes all the way to 14. So when I compare these are very acidic substances, right? They have a higher hydrogen ion concentration. So can you see the number of hydrogen ions is much more than the hydroxide ion? So we get to water then. So these are all acids. Anything less than 7 are acids. And then as we get above 7, we're in the basic. And what do you notice in the bases? A lot of our cleaners are basic substances. So bases need to be respected as well. If you've ever smelled ammonia, it's very strong. Like if you've ever been around people with kids that have diapers in a diaper pail that have been sitting for a while, and that urine converts to ammonia and gives off a very sharp, strong smell. Or if you've ever had a dog that's peed on the carpet and after a couple of days, it's like, what's that smell, right? Or cats. Cats have really strong smell. Yeah, you can tell a cat home, right? Right when you walk in if your cat is not using the litter box appropriately. So bases are slippery and bitter tasting. If you think of bitter, have you ever tasted baking soda? What that tastes like? It's very bitter. But baking soda is great at neutralizing acids. For example, if you have an acid stomach, like if you've eaten a lot of maybe junk food or maybe you're stressed out, and all of a sudden your stomach goes bad right away, you get some bad news, or just something happens, you're in a fight with your boyfriend or girlfriend or a family member or a friend, all of a sudden your stomach kind of goes bad and you stop digesting your food and it feels really sour and you start to get that heartburn feeling maybe. A little bit of baking soda dissolved in water tastes terrible, but you drink that down, that's going to neutralize that stomach acid and make you feel a lot better very quickly. Luckily we have Tums and Maalox and all these better, Alka-Seltzer, that's kind of nasty tasting too, but it helps and tastes a little bit better. Did you have a comment? Yeah, exactly. So that neutralizes that acid pH and it helps the enzymes that help you digest, it helps them work better. Because when our pH in our stomach gets too low, the enzymes for digestion stop working. And have you ever had that when you eat a bunch of junk and then you go to bed and it feels like your stomach is full and it's just not digesting and you're like, ugh, right? Then you take that Tums, everything kicks in, the enzymes kick in, and things move through your digestive tract. And they're not just sitting there in your stomach full. So we can appreciate the effects of these bases in neutralizing acids. Okay, so let's move on then. So the scale goes 0 to 14. 14 is the most basic, has the least number of hydrogen ions in solution, and a lot of hydroxide ions. Another basic ion is called bicarbonate ion. And bicarbonate ion is written as, this is a basic ion. So when it's released in solution, so we said OH was a basic ion. Another one is bicarbonate ion. So this is called hydroxide ion. Hydroxide ion. I'll make this bigger too so everybody can see this a little better. Hydroxide ion and bicarbonate ion. So these are bases. When they're released in solution, they raise the pH. So baking soda is, baking soda is NaCO, Na2, oh goodness have my wrong font going here. Okay, so it's Na2. Oh, what in the heck is going on here? Get out of there. Okay. Na subscript 2 CO should not be this hard. 3 minus. Okay, so that is just simple baking soda. And that bicarbonate ion, this carbonate, combines with H plus in water when it's dissolved, and we get this basic ion that's going to bind up excess hydrogen ion in the environment. So baking soda is an excellent base. It's bitter and will neutralize a low pH. All right, so back to our notes. So when acids donate hydrogen ion, if we throw a base in there, that is going to bind the hydrogen ion and take it out of solution. So when these are free hydrogen ions, that's when we run into trouble. So there's something called weak acids and weak bases. Strong acids, strong bases. If it's a strong acid, it means that, like HCl is a strong acid. When it is in solution, every HCl compound will break up into H plus and Cl minus. It's completely released, it's all of its ions, and we don't see any HCl still bonded together in that solution. They've all broken up, so there's a lot of hydrogen ion released. When we look at weak acids, like carbonic acid is a weak acid, we see it break up into H plus and CO3 minus, but not all of it has broken up into those ions. Some have stayed together as H2CO3, so it's still bonded together and it's not releasing the hydrogen ion. It releases a little bit of hydrogen ion, so that's why it's called a weak acid. And carbonic acid is a weak acid that we find in human body fluids, and it plays an important role. But, well, that's another topic for another course, so we'll just leave it at that. So for your understanding, you just need to know low pH means strong acid, high pH means strong base, and the ions that they release that make them acid or base. Acids release what ion again? H plus, and bases release OH minus, or the other one I wrote, yeah, bicarbonate ion, HCO3 minus. Okay. All right. So what do we care about acids? Well, in the environment, some of the pollutants that we release into the environment from factories, from our exhaust, out of our vehicles, create an acid environment. And when water comes in contact with that, it creates acid rain. And acid rain is anything with a pH lower than 5.6, and that destroys the soil chemistry. It creates an acidic soil, which is going to destroy the ability of plants and forests to grow. So here's just some examples of acid rain, its effects on this forest. You can see it's, you know, it's summertime because the grass is green. It's kind of a pale green, right? Not a healthy color. And then a lot of the forests are destroyed. Yes? 5.6. Anything lower than 5.6, yeah. So when that falls into lakes and streams, that's going to affect vegetation in lakes and streams, and which is going to affect the animals and like plankton and bacteria that are important to lake and water health. It's going to affect that as well. So it's really something we got to pay attention to, and the emissions are what are causing that. So again, factories, exhaust are things that contribute to acid rain. Yes?
So that's like eroding all the like vegetation off the trees.
Mm-hmm.
What would it be that it would do something to like human skin?
Some people that live in big cities that are sensitive already have reactions to acid rain and acid precipitation like fog. Like I went out to LA this summer, And in the morning, it was foggy every morning that was blocking out the sunshine. And it was from moisture that comes from the ocean that picks up all this debris in the environment and just sits there. And then as the sun rises and burns off that precipitation, then it goes away. But every morning is like a foggy morning in LA because of smog. Smog is that mixture of ocean air mixing with pollutants. And some people, when they walk in that smog, they cough, their eyes burn, their nose runs, they're very sensitive. So it depends on the individual. And if a person is a smoker and lives in LA and has a long commute sitting in traffic, the carcinogens that are in smog contribute to lung cancer and triples their lung cancer risk. So people who live in big cities and smoke are, just exposed to that much more chemicals in the environment. So they recommend, sensitive people not live in big cities. And because when I lived in Milwaukee, I had terrible allergies. And then I moved to La Crosse, and I hardly have allergies at all. I have a little bit of fall allergies when the ragweed starts to grow for a couple weeks, but I have literally no allergies now. And La Crosse has some of the cleanest air in the country. I was just listening to something recently about that we've done a really good job at that. But there's some areas that we need to do a little work. Down by Gunderson, the Isle of La Plume, that rotten sewer smell. Have you noticed that? If you get down to downtown La Crosse, there's a sewage garbage treatment plant called the Isle of La Plume right across the river in there, and it really stinks. And is that good for us to be inhaling? I don't think so. I wouldn't want to live in that environment. And there's another one out by Nathan Hill between Woodman's and West Salem. Have you ever traveled that route? It really stinks there too. That's another waste treatment plant. And it's giving that, producing that into the air. So those two little pockets, I wonder if that's contributing to poor air quality because it really smells. Okay, so now we're going to move into a different topic related, but still chemistry, but slightly different. We're going to talk about the molecules of life. And the key word that I want you to write on this slide is that these are organic molecules. And when we say organic, it means they contain carbon, hydrogen, and oxygen. But carbon is the defining atom that makes something organic. The only exception is carbon dioxide. That's not an organic molecule. It's not an organic compound. These are molecule. These are all organic molecules. So sugars, proteins, fats, and nucleic acids. So carbohydrates, examples of carbohydrates, we hopefully are aware of because you've heard of low-carb diets, right? So anything that's a sugar is a carbohydrate. Proteins, meat, cheese, dairy products contain protein. Nuts contain protein. A lot of the different things contain protein. Lipids are fats, and nucleic acids are like DNA and RNA. But they all contain carbon. They're found in living things in different compositions and concentrations. So we'll start with the first group, carbohydrates. Sugars and polymers of sugars. So the simple sugars are glucose. So fructose is another simple sugar. It's just one sugar unit. When we look at it chemically, they're just these special little units here, carbohydrate units. They all have that kind of similar arrangement of carbons, hydrogens, and oxygens. These are the simple sugars, so we can absorb these across our digestive tract very easily. So when you bring in a more complex sugar, like a noodle, which is a starch, long chains of glucose, your digestive system breaks those down into the single units of glucose, and we could absorb that into our digestive tract. We can't absorb anything more complex than these simple sugars. We have to digest them down into simple sugars. Like lactose is not a simple sugar, that's a disaccharide. This we need to digest. And if we can't digest it, it ends up in our lower GI tract and causes lots of problems. So people that are lactose intolerant or have had babies or no babies that have been lactose intolerant, life is a living hell. Because those babies are gassy, they have stomach cramps, maybe diarrhea, maybe constipation. Without the enzyme lactase to break down lactose, that disaccharide, the 2-sugar unit, ends up in the large intestine, the colon, and causes lots of problems. That's why we call it colic. Colic is in the colon, And those babies need to be switched to a different formula if they're not being breastfed to help them deal with not being able to break down lactose. Or if you're lactose intolerant, you can take lactate. It's an enzyme in a pill form. Like if you can't eat ice cream, some people have just an ice cream sensitivity. The fat, the sugar, and the lactose combined, their digestive tract doesn't tolerate that. I'll get to your question in just a sec. When they take that enzyme before that ice cream, they're okay. But other people can't have any kind of dairy product because we need to digest those things down. And it takes energy to digest those things down. So those are a little more complex than the monosaccharides. And the sucrose is something you're familiar with. That's just table sugar. So that's what we put in a lot of our foods to make them taste sweet, candies and desserts and things like that. That's sucrose. Question? Poly means many, like a polygon means many. So a polymer means there's many sugar units bonded together. So like a protein is a polymer of amino acids we're going to talk about. There's many amino acids bonded together to make a protein. So this is not really a polymer yet because there's just 2 sugar units. But when we get to the polysaccharides, many sugar units. So cellulose is the non-digestible polysaccharide that makes up plants. We call this roughage in our diet, right? We need to get cellulose in our diet. We call this fiber as another example of this because we can't digest this. But cows can, termites can, sheep, they can, all those grazing animals, they can eat the grass, break that cellulose down and release the energy in those sugar units. And it's just because of the bond. Look at the bond. Look at the difference between starch and cellulose. So starch is bread, noodles, rice, potatoes. Those are all starch, all made of starch. And just because that bond goes this way versus this way, our enzymes can break this down. We have an enzyme called amylase that can break this starch down and release those sugar units, which can be absorbed by our cells for energy. This we can't break down, so it stays in our digestive tract, creates bulk in our stool, and allows us to pass soft stools. So that's important because it gives bulk to the stool. If we don't get enough cellulose in our diet, then stool becomes hard and sticky, and people are chronically constipated. And that's a big problem here in the US. The American diet doesn't contain all the good, tasty foods that we like, doesn't contain enough cellulose, and as a result, we're chronically constipated. And what's the #1 cancer of Americans in the US? What? Colon cancer. Yeah, colon cancer, because that constipated stool full of preservatives that we like in the American diet, the fast food, Taco Bell, McDonald's, pizza, donuts, chips, right? Chips don't have many preservatives, actually, and that's my go-to for my junk food fix. But, Cheetos and all the other junk that we like to eat, the packaged snacks, that sits in the lower digestive tract against the intestinal wall and causes mutations in that intestinal wall, leading to colon cancer. So if you have a bad eating style, you eat a lot of junk food, and as a mother of 6 children now, I still have younger ones at home, I'm careful to not feed them a lot of preservatives. Like my daughter always wants Lunchables. Can I get a Lunchable? Can I get a Lunchable? Well, not every day, because there's a lot of preservatives in Lunchables, and it's not a good eating habit to develop. So if you've been raised on comfort foods and your parents served you hot dogs and boxed macaroni and cheese and pizzas and a lot of processed foods, it's time to break those habits and go to more healthy, whole foods if you want to reduce your cancer risk colon cancer risk later in life, especially if it runs in your family. Think of your older relatives. Did anybody die of colon cancer? Did anybody have to get part of their colon removed because of colon cancer? Those are things you got to think about to protect yourself and start those habits now, because colon cancer and things like that develop very slowly over time. Yes? Anything that is a plant. So anything that is roughage and hard to chew, anything that's crunchy is going to have cellulose, because it's the structural part, because plants don't have a skeleton, right? So there's nothing to hold them upright other than cellulose. So that's their structural sugar that gives them, so celery, really crunchy, right? Apples are crunchy. So if you want to get the benefit of apples, you have to eat a whole apple. Apple juice does not have any fiber. You need to have the apple itself, right? And that's why they tell people, you know, don't rely on multivitamins because you're missing the fiber that's in the foods that contains those vitamins. But vegetables are expensive. That's the bad part, especially in Wisconsin. If you go to the produce aisle, a lot of the vegetables or fruits that we enjoy are expensive in the off season when they're not grown locally, right? Strawberries have an awesome amount of fiber. Strawberries are one of the top 10 most healthy foods you can eat, and a lot of people like strawberries, right? So that's a really good choice in fiber. So oranges are excellent in fiber. So if you're someone who's chronically constipated and you have bad gut a lot of the time, you feel bloated and you're not moving your stool through, strawberries, pineapples are really good. Bananas, not so much. Think of a banana. Is it crunchy? Bananas are actually constipating, so people shouldn't eat a lot of bananas if constipation is a problem. All right, so glycogen is another complex polysaccharide. This is what we store. So plants store excess glucose as starch. So that's what they use for energy, and we eat the plants to get that energy. So starch, again, is rice, potatoes, breads, noodles, all that stuff. Glycogen is how we store excess glucose in our blood. So when you eat food and there's excess glucose floating around after digestion, it'll be stored as glycogen in your liver and muscle cells. So that's where it's stored, liver and muscle. And then the excess goes where? Unfortunately, where does the excess? Fat. We store the excess as fat. Our body never wants to get rid of excess glucose because there might be a famine. So we're always preparing for famine. I haven't experienced a famine in my years on Earth yet, but my body is still prepared, so we always store excess glucose as fat. Now, if you are someone who exercises, your body creates more glycogen stores than someone who doesn't exercise. So if you're lifting weights, still your muscles will create more glycogen stores to accommodate the energy needed to lift those weights. If you exercise, and it doesn't have to be killer exercise where you're huffing and puffing on the treadmill or bike. It could just be simply raising your heart rate up a little bit into that fat burning zone and just doing simple exercise, like going for a walk at a brisk pace, not just strolling along, but at a brisker pace. Your body's going to build more glycogen stores. So when you sit down to eat and you have that excess glucose floating around, it's going to go to glycogen before it goes to fat. And that's why people will tell you, oh, I lift weights and I can eat more because of that. And that's true because our body builds glycogen stores whenever we exercise or do anything with our muscles that's in excess. So that's less that goes to fat then. The more glycogen stores you have, the more glucose can fill those shelves and not go to fat. The same thing is true when you're not eating then. If you have glycogen stores full of glucose, you're going to release that glucose during exercise, and you don't have to necessarily have food in your belly prior to exercise because of those glycogen stores. So it's the body's way of preventing starvation as well. And chitin is another sugar that we see in the cell walls of mushrooms and fungi. That's their supportive structural polysaccharide. So chitin, because mushrooms don't have fiber. Unfortunately, you can't get cellulose out of mushrooms, and they're not green. They don't contain chlorophyll. Yes? Yes, yep. The other place we find chitin is in insect shells, exoskeletons. Anything that is an invertebrate that does not have an internal skeleton contains chitin. So that crunchy sound when you step on a beetle, that's chitin in that exoskeleton. And like you said also, the crab shells, those are all chitin. So that's a structural polysaccharide among animals, insects, and fungi. So be able to know examples of each of these polysaccharides and where we would find them, okay? So plant polysaccharide, we said, is starch. It's a storage for energy. And we store our excess glucose as glycogen. And like I said, cellulose is a structural polysaccharide. So who can digest cellulose? Again, it's cows and termites are two good examples. Chitin, we already talked about. It's also used to make surgical thread. The next group of organic compounds is our fats. And let's take a quick break and we'll come back and start talking about that topic. All right, so fats are also called lipids. They're made up of not polymers or monomer. A monomer is the little building blocks of a polymer. So if the polymer is starch, what did we say the monomer? What was the building block of starch? No, we just talked about carbohydrates, right? Starch is a polysaccharide. Yeah, what's the building block of starch and cellulose? Glucose, yeah. Glucose is the building block. It's the monomer. Mono means one. Poly means many. So the polymers is starch. The monomer is glucose. That's what builds up starch. So what's the repeating unit in a fat? Two different things, glycerol and fatty acids. So you've heard of maybe omega-3s and omega-6s, fatty acids, right? Have you heard of those things? Fish oil, which is the good one? Is it omega-3s that we want a lot of or omega-6s? Do you know? Yeah, omega-3s are the healthy fatty acids that we want a diet rich in. So fish oil has omega-3s, olive oil has omega-3s. A lot of those healthy plant oils that you hear a lot about have those really good fatty acids. And we can use those as fuel. And the brain does well when we have a diet rich in these omega-3s. So what do omega-3s do for us? Let's talk about that. So omega-3s fight inflammation. So that's really important. So people that have a diet rich in omega-3s have less achiness, body aches, joint aches, just tissue damage in general. It helps keep our blood vessels. It helps us process cholesterol, so it reduces cholesterol. And again, it's a good fuel for the brain, and the brain actually functions better with a diet high in fatty acids. People find that they're better students, taking tests and remembering things and just being more mentally alert and on fire when they have a diet rich in omega-3 fatty acids. Yes? Those, hopefully people are bringing in healthy fats, yeah. That's what they recommend. A good ketogenic diet is using olive oil and fish and, not just eating bacon and those bad fats. So the bad fats are the omega-6s. Omega-6s we find in cheeses, fatty meats, like, again, a diet high in pizza, chicken wings, fast food, burgers. Those have the bad fats. So the white you see in burger, that's animal fats. Those are saturated fats. Those are high in omega-6s. And what do omega-6s do? They promote inflammation. People that have diets high in omega-6s have low energy and lesser mental functioning. So people have made huge changes in their diet and felt the difference when they switch from a diet high in saturated fats to a diet higher in unsaturated fats, and their energy level goes up, their mental functioning goes up, and the achiness and number of headaches they get goes down. So omega-3s, there's a lot to be said for that, and you can buy fish oil orange flavored so you don't have that nasty fish residue. Like if you take just a regular fish oil and then you burp after that, you burp fish. Who wants to burp fish at 8 in the morning, right? Not me. I don't want to be sitting next to someone who does. So the orange flavored fish oil is really good. Otherwise, there's other types of, those good fatty acids in olive oil. But again, trying to get that in your diet when you're a busy college student. And for me, as a busy mom and working a bunch of different jobs, I just take 2 fish oil in the morning, the orange flavored fish oil. I get them at the co-op because they don't contain mercury. And I find when I'm taking my fish, because I get busy and I run out of fish oil and I don't go and get it, you know how that is. I can feel the difference when I'm not taking fish oil. I have body aches, I have more headaches, and when I'm teaching, I'm not as, quick on pulling information that I normally remember. All of a sudden I'm like, what was that term again? And I'm looking in my notes. But when I'm taking my fish oil, I remember things better. And even when I'm young, it's not even an age-related thing. Even when I was young and I was pregnant, I would find when I was pregnant, I couldn't teach. The words weren't coming, and I had the pregnancy brain they talk about, because the brain actually shrinks during pregnancy as the baby is pulling, the developing baby is pulling fatty acids. For its own development, it's taking it from the mom. So for mothers to take fish oil when they're pregnant, it's a really good idea. And I found a big difference when I did. Yes?
So those fat that normally unsaturated,
That's a really good question. Typically, fish oils are not fatty, because if you look at fish, you don't see that white saturated fat. Yeah, it's the omega-3s that are typically liquid at room temperature. That's the unsaturated fats. Yeah, good question. So, and the fish oil that you see in the little capsules, it's liquid in there at room temperature. Yeah, typically any fat that's solid at room temperature is a saturated fat, that white that we see in the foods that we eat. Yes. 3s, yeah, omega-3s. Yeah. Yeah, it's not going to, repair a significant injury, but it's going to help. Yeah, it's going to help. Like I find, just because I beat my body with a lot of sports when I was a young person, I find that when I'm not taking my fish oil and I get out of bed in the morning, it's like, just everything kind of aches. But when I'm taking my fish oil, I get up and I'm like, I feel pretty good this morning. So it makes a difference. It definitely makes a difference. Yeah, it would help. Yeah, it would help. It does thin the blood as well, a little bit as too. Ibuprofen, Advil, those kinds of things are anti-inflammatories too, and they also thin the blood a little bit. So does aspirin. Aspirin is in the same category as ibuprofen. So fish oil is a little bit like a natural ibuprofen. So it does thin the blood a little bit. So the benefit of that is it prevents blood clots as well. So it lowers that risk a little bit. So, but again, some people are a little sensitive to fish oil and it disturbs the gut and can give some people diarrhea. So this depends on the individual. But if a person tends to be a little constipated, then fish oil is good for that as well. So there's a lot of benefits of these good fatty acids. And it doesn't just have to be fish oil. Like I said, there's other healthy omega-3s that we can get in our diet. So saturated fats, omega-6s. Unsaturated fats are typically made up of those good fatty acids, the omega-3s. All right, so why do we need fats in the body? Energy storage. So it's important that we have some fat on our body. So in the event we get sick, right, and we can't take foods in, we have a little bit of storage. And another benefit is cushion. If a person is really thin and they bump themselves, they're more likely to get injured, right? Like we don't have a lot of fat on our shin, right? And if you bump your shin, it really hurts, right? We have a lot of fat on our backsides, so we sit on our backsides a lot, and it doesn't hurt when we plop down because of that cushion. So it provides an important function of just cushioning body parts. Animals that live in really cold environments rely on fat for insulation. So fat is a really good insulator as well. So energy storage long term. So anytime we bring in excess glucose and we fill our glycogen stores and we still have this excess glucose floating around and we're not moving and using it, it's going to store as fat for long-term storage. And the body has an unlimited ability to grow fat cells. So we have a set number of fat cells. Once we're done growing and we're done with puberty, we have this set number of fat cells we've developed in our childhood. And those get bigger or smaller depending on how much glucose we're needing to store. So you've seen the documentaries or the reality shows. My 400 or my 600-pound life or something. Wasn't there one years ago that was that? And that's just an example of the body's unlimited ability to continue to get bigger and bigger and bigger and bigger until people die from obesity. And what they typically die from, because being a nurse, I see some of these patients in the hospital, is respiratory failure, because the lungs cannot keep up and supply oxygen to this huge body mass. And another thing that they pass away from is heart failure. The heart has to pump blood to this large mass, and after a while it just fails because it can't keep up with that large mass. So how people get into that cycle is, abnormal relationships with food, just bringing in food more and more and more, and the stomach starts to stretch. And once the stomach gets high volumes of food in it, it stays at that resting length of an overstretched stomach. And then as it empties, it starts to tell the individual we're hungry, because it was full with this much, now it's starting to shrink a little bit and giving hungry signals. So that hungry signal then causes that person to eat and fill it up to fill that large stomach again. And that's why you look at people that are very, very large, and you look at the size of the meals they're bringing in. They can eat a large pizza themselves, a carton of ice cream for dessert, and that's just a lot of calories, right? And that feeds those large fat cells that causes them to get bigger and bigger and bigger. So it's really difficult when someone gets into this spin of having an overstretched stomach, large meals, and no activity. How do your joints feel when you're a large person? Your joints start to break down. The knees are not meant to carry a large body mass. And the number one reason patients come in for joint replacement is carrying a large body mass over a lifetime. So if you look at maybe relatives or people that you know that have had their knees replaced, are they overweight? Or maybe they had just bad knees from football or overuse. That's another class of patient. But unfortunately, the large majority of knee replacement surgeries are the result of a large body mass over a lifetime. Yes. Oh my goodness. Yeah. Mm-hmm. Yeah. Yeah, you wonder if their diet was healthy or not. Mm-hmm. Right. Yeah, and eating disorders is a big problem. So we try not to focus on weight as much as just body characteristics and making sure that, people are within a normal body weight for their body type, but not focusing on, by society's criteria, what looks good, right? Because I taught a health class at UWL, and we had some girls in the class that were 19, and by society's standards, they looked healthy, right? They were thin and didn't have any excess body fat. But when we did strength testing of those women, they were very weak, very, very weak. And there's a large group of women in the nursing home right now that were very thin all through their lives, but they're in the nursing home because with aging and no exercise and a poor diet, they have no strength. And they have osteoporosis, and maybe they've fallen and broken bones, and they have no strength. So if you want to be thin, that's a good goal, but as long as it's a healthy thin and it's counteracted with strength training and weight-bearing exercise, so you keep your bones strong and you're not at risk for osteoporosis, because being overly thin is a high risk factor for osteoporosis, and that's, takes away from health as well. So again, fat storage, long-term energy fat storage, also insulation. That's not listed here, but insulation is important. Animals that live in cold climates rely on their fat for insulation, and also cushioning our vital organs. So for example, people that drop weight really fast due to illness or eating disorders can actually cause a kink in their ureter, which drains urine from the kidney to the bladder, because the kidneys are surrounded by fat, and if they lose too much fat, the kidney drops and kinks the ureter and can cause an impairment in the urinary tract or urinary function. So Also around the eyes, there's a rich source of fat. Have you ever noticed after a long flu or illness or not being able to eat that your eyes look kind of sunken in? You can tell people that have been ill because their eyes get kind of hollowed out. There's a rich source of fat behind the eyeball. So this is what these fatty acids look like. This is what saturated fats look like. This is a triglyceride, so we can see the three kind of chains of these carbons that come off the glycerol. So here's the glycerol, here's the fatty acids. This is a triglyceride. These are found in saturated fats. These are the bad fats. So this is a healthier fat. This is palmitic acid found in plant fat. And this is the bad fat. This is what our adipose looks like. This is the white we find in hamburger meat, has the triglycerides. So we want to limit that. There's other types of fatty acids that are important. For example, this is our cell membranes. This is what the outer membrane of our cells looks like. So they contain these phospholipids. There's a phosphate group with fatty acid tails. So here's the phosphate group. You see the yellow? And it has these fatty acid tails. So phospholipids are a class of lipids that are important in cell membranes. So this is something that you would see in a lecture quiz. Which of the following is a lipid, or which of the following is found in cell membranes, or what is the importance of phospholipids? That might be a lecture quiz question, and you would know that it's part of the cell membrane. So the phosphate is a charged molecule, so it attracts water-soluble substances to the cell membrane. But those substances can't enter because the inside layer, these fatty acid tails, lipids are nonpolar. They form nonpolar covalent bonds. They're not charged. They don't allow things through that are water soluble, that are charged. So we know that water and oil don't mix, right? When you have salad dressing, the vinegar and oil salad dressing, you have to shake it up, right, to get it distributed before you put it on your salad. Well, that's this oily core of our plasma membrane. It does not allow things through. It's selectively permeable, our plasma membrane. So there's little protein channels in here that allow certain things that are water soluble to pass through selectively. Only things that can dissolve in this fatty core are things like alcohol. That dissolves in fatty acid or in oily substances, nonpolar substances. Carbon dioxide and oxygen can diffuse readily through this fatty core, but sugar cannot, so glucose cannot pass through. Ions like salts cannot pass through. Proteins cannot pass through. They need special channels or carriers to get through. And we'll talk about that when we get into the cell. But all you need to know is the plasma membrane contains lipids, phospholipids. It's what our plasma membranes are made out of. It's the brick and mortar of our cells. And this part likes water-soluble substances, so we say hydrophilic. Hydrophilia means to love. So water-loving head, which means it attracts water to the surface and any charged substance. And the core is hydrophobic, which means water-fearing. It repels water and any water-soluble substances. Another group of lipids is steroids. Steroids are things that contain this fundamental structure called cholesterol. Cholesterol has this four-ringed structure. So you can look at all these steroids, see how they all have that four-ringed structure, but a little different in some of the atoms that come off of that four-ringed structure. But that's the fundamental characteristic of all steroids, is this four-ringed cholesterol. So cholesterol is important because we also find that in the plasma membrane. It gives a little stiffness to the plasma membrane. We find cholesterol embedded in here. We'll look at that in more detail when we study the cell. So cholesterol is good for that. This is estrogen. Estradiol is estrogen. That's an important hormone that makes girls girls. And testosterone is the hormone that makes men men. So they wouldn't look like men if they didn't have testosterone, and women wouldn't look like women if they didn't have estrogen. Progesterone is another female hormone that's important for pregnancy and the uterine lining. Cortisol is a hormone that is a stress hormone that is released, unfortunately, in people that have chronic stress, they end up having high cortisol levels, especially in the morning. Cortisol levels are highest in the morning if we're living under kind of a stressful environment. And it causes us to deposit fat, causes weight gain, fatigue, inflammation, not good for long-term stress. And aldosterone, this is another hormone. It's released by a gland on the kidneys that helps us control our fluid balance. But you don't need to know the functions of these hormones. You just need to know examples. Okay, so if I say, which of the following is a steroid? You should look for one of these listed in that multiple choice question, and there you go. Okay, or I could say, which of these is a fat? And I could say steroids, and you would know that's an example of a fat. Okay, or I could say progesterone is an example of a, you could say steroid, or a lipid, depending on the level of the question. Proteins, another class of organic molecules. These have many, many functions in the body, a lot of different functions, and we are made up of proteins. So our skeleton, our muscles, our skin, the structure of our body is protein, so very, very important for structure. So if we look at the dry mass, get rid of all the water in the body, so we just have a pile of stuff, matter that is the human body, half of that is protein. So when you look at the structure of us, our skeleton and muscles and things, that's all protein. So we need this for structural support, transporting substances, storage, cellular, I mean, lots and lots of functions for proteins. So our immune system, antibodies that we make when we're exposed to different things in the environment that are foreign, like viruses and bacteria, we make antibodies against those, and antibodies are proteins. So really, really important for the immune system. A lot of our hormones that we produce in the body are proteins, like insulin is a hormone that's made of protein. Any enzyme in the body is a protein. So enzymes are really important for all the chemical reactions that occur in the body. Those are proteins. So it's important that you know examples. Like I said, enzymes are an important one. And this list here gives us just examples of different proteins. So digestive enzymes are proteins, collagen, anything that we use, you know, for structure and support in animals are proteins. Storage proteins we see in egg white, milk, plant seeds, those are storage proteins. Transport proteins, hemoglobin transports carbon dioxide and oxygen, very important. We talked about insulin, that controls blood sugar. We have receptors on our nerve cells that are made up of proteins. Our muscles are made up of protein, cilia and flagella that help single-celled organisms maneuver their environment. The flagella we know is on sperm. Cilia lines our respiratory tract, our airways, and I've talked about antibodies. So really, really important organic molecule are these proteins. So enzymes are proteins. So you have an enzyme like sucrase, for example. It needs to digest or break this bond of sucrose. So we call sucrose the substrate. And it binds to the enzyme, and that enzyme breaks that bond and releases the two monosaccharides that make up sucrose, which is glucose and fructose. So it breaks that bond, and that enzyme is reused again. So the enzyme is not used up in the reaction. It just interacts with the substrate. In this case, the substrate is sucrose, breaks the bond, and it can be reused over and over and over again. Exactly. Exactly. Yes. No. No. Exactly. Yeah. Yeah. I mean, we're not going to go into great detail in this list, but a good example for me would be enzymes belong to which group of organic molecules. So that's a real kind of basic thing. These are just specific examples. Yeah, you don't need to know this list. Good question. Okay, so all enzymes are proteins. So when you look at a protein, it's made up of an amino acid, and that's the building block. All enzymes are proteins. Yeah, all enzymes are proteins. And when we look at the chemical structure of a protein, it's made up of the building block, the monomer. So proteins are a polymer of amino acids. The building block are single amino acids bonded together. And proteins are charged molecules, so they are water soluble. So if we look at, for example, this is the backbone of a protein. The side chains come off of the different amino acids that make up a protein, and those differ a little bit from one another. But all these amino acids are bonded by a special covalent bond, and that covalent bond is called a peptide bond. So think, peptide starts with a P, protein starts with a P. So we find peptide bonds in proteins. So you have amino acid, amino acid, amino acid, 3 of them in a row. What connects the 3 amino acids are peptide bonds. And proteins are long chains of these amino acids. So here's some kind of cool examples of proteins, structural proteins. So the silk fibers released by spiders making a spider web is a special structural protein. And the shape of these proteins is very unique. And one specific shape of a protein is called the beta pleated sheet. And you don't need to know the detail of that. That's, more detail than you guys need to know for this course. But it's very unique and repetitive. So the arrangement of these amino acids and how they interact with one another give the proteins a specific shape. And that gives the advantage to the spider to have this nice arrangement to catch insects and do their job. Hemoglobin has a very specific shape, and when it has the correct shape, it's nice and round. It can flow through our capillaries, releasing oxygen, picking up carbon dioxide, and keeping us healthy and well oxygenated. But if you have a disease called sickle cell anemia, and one of the amino acids in your hemoglobin is mutated and is a different amino acid, when oxygen levels get low, your hemoglobin molecules change shape, and that changes the red blood cell shape, and they get this sickle shape. And as a result of that, they clump together in the capillaries, and they cause massive clotting. And people with sickle cell anemia have trouble with blood flow, and they have to get to the hospital and get blood transfusions, and it's a lifelong disease because of one amino acid that has been replaced in that protein, causing that shape of that hemoglobin molecule to change in low oxygen environments. So if they go to high altitudes, they can have a sickle cell crisis. If they have a bad lung disease and they're not getting enough oxygen through normal breathing, they have a sickle crisis and they end up in the hospital. Yes?
Did you fix that at all with warfare?
No, because it's a clump. It's not a blood clot. It's a piling up of red blood cells. No. Right, yeah. Yeah, I'm not sure, honestly. I haven't had a patient with sickle cell anemia. We see a lot of this. It's more common in people of African descent. So we see it in big cities where there's a large African American population. And we don't have that here in La Crosse, so I haven't dealt with a patient with that. Good question, though. So a normal protein kind of folds in on itself and has a very specific shape. And when we denature it, and then we can denature proteins with things like radiation, acids, changes in pH. Heat denatures proteins. For example, egg white is a protein. If I throw it in a pan and heat it up, it looks really different, right? It's rubbery and white. It starts out slippery and transparent, that egg white. When I cook it, it's white and rubbery and has a texture, and we enjoy egg whites, right? That's a denatured protein. I can't get that back again. If I threw a strong acid on an egg white, I could see it cooked the same way. No temperature change at all. Just put a strong acid on that egg white, it would turn that white rubbery consistency because I've denatured the protein. Last group of organic molecules are nucleic acids, and these are DNA and RNA. So again, made up of repeating units. These are polymers, and the repeating unit is a nucleotide, and we'll talk about that in a minute. But DNA is important for protein synthesis. So the recipe for making proteins is in the DNA molecule. So what we need DNA is protein synthesis. And RNA helps make the protein. So RNA works with DNA to make proteins. So where does that all occur? On the ribosome. So when you think about the function of nucleic acids, it's protein synthesis, which occurs on the ribosome, which is an important organelle in the cell. So this is key. So the repeating unit is a nucleotide. So that's what this is. It's a 3-part unit, a phosphate, a sugar, and a nitrogen base. So that's what makes up the nucleic acid. So if I look at, this is an example of a single-stranded, this would be like RNA. So we have a phosphate, sugar, phosphate, sugar, phosphate, sugar, running down this main strand with nitrogen bases directed off of that. So the sugar in DNA is called deoxyribose, and the sugar in RNA is called ribose. So that's the sugar piece. And then the nitrogen base, there's a couple of different types. If it's DNA, it's adenine, guanine, cytosine, and thymine. So that's in DNA. So the only difference between RNA and DNA is the sugar and one of the nitrogen bases. We see uracil in RNA and we see thymine in DNA, but the other 3 remain the same whether it's DNA or RNA. So the repeating unit is, again, this nucleotide. Now we're going to go into a lot more detail about DNA. We're going to build the DNA strand, so we're going to go, in more detail later. So this is what DNA looks like. So the sides of the DNA, it's a coiled, double-stranded structure. The sides of the DNA ladder are sugar and phosphate. So that's this part. This part forms the sides of the DNA ladder. So if I untwist DNA, it looks like a ladder. And the rungs of the ladder are the different nitrogen bases. And these nitrogen bases are hydrogen bonded to each other. That's what holds the 2 sides of the ladder together. And adenine is always bonding with thymine, and cytosine always bonds with guanine. So if I told you one side of the DNA ladder was C, G, A, T, C, what would the other side be? G, C, T, A, G, right? Because C always bonds with G and A always bonds with T. So if I know one side of the ladder, I can always predict what the other side is because it's hydrogen bonded to a nitrogen base that's complementary. We call that complementary base pairing when we combine or when we can predict the other side of the DNA ladder based on the nitrogen bases that extend off. So these are the rungs of the ladder, right? The nitrogen bases are the rungs of the DNA ladder, and the sugar and the phosphate, that doesn't change. That is along the side of the DNA ladder. So when we look at DNA then, your DNA defines all the proteins in your body. And structurally, we're made up of proteins, right? So when I look at a person's face and hair and body type, body structure, that's all written in the code of DNA. So every cell in our body in the nucleus has DNA that has the blueprint for making another one of you, right? So that's why we use DNA fingerprinting, we call that. Is all we need is hair or skin cells to find out an individual's identity. If they've ever committed a crime before, we collect DNA evidence, and then if we see those things at a crime scene, we can enter that into the database and we can identify who the criminal is based on that. So take-home point from that is that if a person is attacked, raped, it's important, if you ever give advice or if you know someone this has happened to, it's very important that individual go to their local ER and they can gather evidence and identify who the person was that attacked them. They can, unfortunately, when people have been killed, they've identified it. They can find it with semen samples that are present on the individual. They can look for samples of skin underneath the nails. So if someone is wrestling with somebody and scratches them and gets the skin under the nails, they can take that DNA evidence and link it to that individual. So it's really important that people be seen if they've been sexually assaulted or raped, so they can gather the evidence they need to hold that person who did that accountable. All right, so that concludes the discussion on the chemistry of life. There is a Quizlet. Oops.